Yeah, good afternoon, ladies and gentlemen. Are your transformers prepared for the future? How to assure grid reliability and prepare transformers for extra loading. This afternoon, we want to discuss this with you. Our agenda, we will start with the future grid challenges and, of course, its impact on transformer loading. And we will discuss, of course, also maintaining grid reliability and resilience. My name is Stefan Tenbohlen, and I have the honor to chair this afternoon session. I received my Dr. Ing. degree from the Technical University in Aachen and started to work with Alstom short transformatoren in Germany. And I was responsible there for the electrical and mechanical design department. In 2004, I was appointed to a professorship at the University of Stuttgart, and I'm heading the Institute of Power Transmission and High Voltage Technology. We are doing research in high voltage technique, power transmission, and electromagnetic compatibility. The other speakers are Peter Grobmeier. He received his diploma of electrical engineering from the University of Applied Science in Regensburg. He has a quite impressive career. So he worked with SGB Suite. He was also with Doble Engineering, and now he is head of European sales at FISO Technologies.
Hello.
Second speaker, hello Peter. Second speaker will be Roberto Fernandez. He is an experienced electrical engineer who has spent most of his career on the transformer design field and R&D activities focused on the magneto-electric and thermal design of a wide range of transformer applications. He is currently the regional technical leader for Europe and Turkey at Cargill Bioindustrial. Hi, Roberto. So, are your transformers ready? You know, in 2018, renewables made up 26% of global electricity generation. That's expected to rise to 45% by 2040, which this is given in a global status report of renewables in 2019. So, what are the challenges? Securing sustainability for future generations should be, of course, main goal for mankind. This means, of course, that high voltage has to be green. The effects of climate change show that measures to reduce CO2 emissions are of enormous importance. And this brings also a lot of people on the streets, increasing the pressure on politicians to really decide on measures to reduce CO2. So for high voltage, this means the development of new materials and devices that enable low emission or emission-free production and operation. This is, for example, or some examples are replacement of SF6 in gas-insulated switchgear, use of vegetable oil as an insulating liquid, which can replace the fossil mineral oil, use of cable systems instead of overhead lines, and of course also higher loading of components. In this figure, you can see the loading of a wind farm transformers for 2 days. Yeah, so the lower black curve shows this loading. You can see that during this 2-day interval, we have quite high loads of 120% on these transformers. We have also quite strong changes of the load, so a quite strong dynamic loading. Here we have here a decrease from 100% to almost 0 and back to 100% in a very short time. So the new operation scheme of these transformers is characterized by emerging peak loads and a quite high dynamic load change. And this high load, of course, results in increased temperatures in the transformer. In the red curve, we have the measured top oil temperature of the transformer, which does not seem so high at the first glance, because we have there quite low ambient temperatures at that time. But if we calculate based on load and top oil temperature, the hotspot temperature, so the hottest point in the transformer, we can see that we have already there quite high temperatures. But not only the integration of renewables, also the integration of electric vehicles bring new challenges on electrification. In the upper figure, you can see the load demand of households, which is a blue curve, and additional in the green curve, the load demand of electric vehicles. And especially in the evening, when people come back from work and start to load their electric vehicles, you have a quite high demand for a household. Yeah, more or less, the demand is doubled by the use of electric vehicles. We calculated how many electric vehicles are needed to bring the transformer to 100% of load. This is shown in the lower figure. So you can see the amount of electric vehicles per household, and the curves show, dependent on the loading power, the load on the transformers. And let's say if we have a three-phase loading, which is the green curve, with and if we have one electric vehicle per household, the transformers are loaded with 100%, which is of course the absolute limit. And the announcement of a lot of car manufacturers says that they want to stop the manufacturing of fossil fuel vehicles in the next years, and therefore this situation will definitely occur. Furthermore, of course, not only the substation transformers, but also the feeders will be significantly higher loaded. And we should not forget that, of course, fast charging facilities at motorways require an extension of the grid. But also electric vehicles and renewables have a strong impact on the power quality. We can see in the upper graphs the number of transients and the total harmonic distortion due to loading of electric vehicles. And we can see that during the day, when we have a high loading demand, also a lot of transients occur, transient overvoltage occur in the network. Also, total harmonic distortion is increased by the loading current. Photovoltaic feed-in also causes harmonics, which is shown in the lower graph. Yeah, so during noon, where we have a strong photovoltaic feed-in, we have also here quite high harmonics. And these harmonics and resonances can lead to hotspots within the transformer insulation system. So overall, we can say we have a higher loading, which brings also higher temperatures to the transformers. This, of course, raises the question, why is temperature so important for the transformer? And I want to give this question to Peter, who wants to show us some slides in that respect.
Thanks a lot, Stefan. So the life of a transformer is related to the life of the insulation material. And life of insulation material is directly related to temperature. And which insulation material do we have in a transformer? So we have, in general, we have paper and oil. We should look at the paper more carefully. Why? Because you can change the oil during the lifetime of the transformer several times, but you cannot change the paper. This means if your transformer is 40, 50 years old, this means the paper inside the transformer is also 40, 50 years old. So let's have a look at the test from the IEEE, which you see on this slide. So just imagine this is the paper in the area of the hotspot. You see at 170 degrees Celsius, and after 500 hours, the paper in mineral oil has already changed its color. FR3 fluid is still good. So then if you go to 1000 hours, the paper in the mineral oil has already lost its insulation. So the IEC says also when the paper has lost 65% of its tensile strength, this is the end of life of the insulation and also the end of life of the transformer. If you look at 2000 hours, the paper is destroyed. 4000 hours, it's just powder. So actually it's not the load of the transformer which reduces the lifetime. It's the corresponding temperature which has a direct impact on the insulation. So if you could go the next slide, please. Here you see a graph. I mean, the weakest point in the whole insulation chain is the hotspot. So this is why we talk that often about the hotspot. And this curve shows the hotspot temperature, and it says overheating of 5 degrees Celsius will reduce insulation life by an average of 25%. And overheating of 15 degrees Celsius will reduce insulation life by an average of already 50%. And now looking at renewables, you can handle dynamic load. This is no problem. You can handle the unpredictable reverse power flow. You can overload your transformer as long as you control the temperature. And to control the temperature, you need to know the temperature. So knowing the temperature and controlling it is the key. That's why the temperature is so important. Today, more than it was used to be many years back, when the transformers were in general loaded at 30-40%, and there was no huge dynamic load. Thank you.
Yeah, but we have already traditional temperature indicators, so why should I use another system?
That's true. So, I mean, it's nothing new if I tell you that temperature inside a transformer is important. I mean, monitoring the temperature is nearly as old as the transformer itself. So let's have a look at a few methods which are available on the market for monitoring the temperature. You have on the left side, the oil temperature indicator is just measuring the temperature, the oil temperature inside the transformer. Then you have in the middle, you have the winding temperature indicator, and on the right side, you have the direct temperature monitoring over fiber optics. So the last two ones are telling you something about the temperature of the winding. So let's compare those two methods on the next slide. You see both methods. So the pictures on top, you have the direct temperature monitoring, and on the bottom you have the winding temperature monitor indicator. So what's the principle of operation? For the winding temperature indicator, it's an indirect thermal behavior simulation. So you have just a sensor measuring the oil temperature, and you're measuring the load of the transformer. And if the load goes up and the temperature goes up, this is running through an algorithm, and it tells you what the temperature of the winding might be. With a direct temperature monitor, you're inside the winding and in the hotspot area, and you're measuring directly the hotspot temperature. Immunity to EMI with a winding temperature indicator. There is no immunity with a direct temperature monitor or fiber optics. It's completely immune just because there is no current running. It's just light, which is running through the sensor. Thermic lag effect of the transformer oil, significant from the winding temperature indicator, and it's negligible for the direct temperature monitor. Since the response time between a few minutes and up to 15 minutes, plus the lag effect of the oil for the winding temperature indicator, and only 500 milliseconds for the direct temperature monitoring. Recalibration needed for the winding temperature indicator and not needed for the direct temperature monitor. So imagine you want, or you have to drive your transformers to the temperature limits. It's nearly impossible with the winding temperature indicator. It's not accurate enough, and it has very long response times. But you can do it with a direct temperature monitor. So you can, let's just assume the sun is shining, the wind is blowing, and then you ask yourself the question, what do I do with my transformer? It's loaded at more than 100%. Do I throttle it and lose money, or do I let it run and risk the destruction of my transformer? You can overload it when you know the temperature. So you can go up to the limits of the maximum allowed hotspot temperatures and control your transformer and overload it. So it's a controlled overload. Yeah.
Thank you. Now we know how to measure the temperature more accurately to prevent, let's say, fast aging of the paper. But can we also influence the paper degradation rate? I would like to ask this question to Roberto.
Oh, thanks. Well, yeah, as we know, the two major problems for insulation and transformer are moisture and temperature. And here in this video, we are seeing just an accelerated aging process of a transformer. On the left side, you can see a transformer mineral oil field that has reached the end of life. You can see how the insulation and the paper has become dark and brittle, as we saw in the pictures at the beginning. And on the other side, on the right side, you have the same transformer filled with FR3 that under the same loading and circumstances just consume around 12 to 15 lifespan of the transformer. And this is because the cellulose age more slowly on FR3 fluid, between 7 and 8 times slower. And as I said, the second point that make the degradation of the paper running faster is moisture. And new transformer filled with mineral oil has a moisture content of insulation around 0.5%. When it has working from few years, it starts to rise to 2%, and at the end of life, a typical value is above 3%. This is because the water is a subproduct of the degradation of the paper. So the paper degrades, it generates water, but these waters also accelerate the degradation process. So we are in a circle of degradation. It's what we call a self-induced reaction. And this is not happening on FR3 because with FR3, the moisture content on the paper is between 0.5 to 1% during the complete lifetime of a transformer. We will see how this works on FR3. But it's also important to note that the reason to dry a transformer is not only to extend paper life. The most important one is the dielectric reason, because a wet paper has a lower dielectric, a worse dielectric behavior related with a dry. So with FR3, we can maintain a good dielectric condition during the complete lifetime of a transformer, increasing reliability, as we spoke at the beginning. And well, here, this video that we just saw, it shows how this water that is generated on the degradation of the paper, because the FR3 fluid has a higher moisture content, can absorb higher moisture content. migrates from the insulation, from the solid insulation to the liquid part, and it is consumed with FR3 fluid. The molecules of FR3 are triglycerides, so when the water reacts with that molecules, it creates what is called free fatty acids, that are long chain of acids that are meal acid is a long chain and pretty stable molecule that do not affect with the other components of the insulation. And this has an additional effect. It is a side effect. It's the transesterification, meaning that this free fatty acid reacts with the oxygen that connects the cellulose chain and protect the cellulose to be attacked by water. But again, this is a side effect. The most important part of FR3 is the continuous drying process of the solid insulation.
Yes, so we learned that it is beneficial for the lifetime of the paper. But of course, then we can say that maybe the increased temperature limits allow us for extra loading capacity. Is that possible, Roberto?
Yeah, absolutely. From the design point of view, there is like a rule of thumb that say that for each degree of increase in the average winding temperature rise, you get an increase of 1% in the load of the transformer, the capacity of the transformer. Of course, it's a little bit conservative rule, and designing a transformer is something much more complex than what I'm saying here. But it gives us an idea that this FR3 fluid with the paper increasing temperatures, which is also accepted by standards, give us a plus 30 degrees in increase on the operational temperature. And this can lead to an increase of 30% in the added capacity. And if we can move to the next slide, I want to put this in some perspective. That is, if we see two lines, the upper one in green is a transformer designed and filled with FR3 fluid, and the lower one is the same transformer filled with mineral oil. If we think about the loading capacity, sorry, if we have a 65 key traditional transformer design, we have that orange part which reflects this 30 degrees increase that's allowed by the standard in the capacity of the transformer without jeopardizing the nominal life of the transformer. It means we have an added capacity of the transformer. A second part is the red one, that is the overloading capacity of the transformer. The standard allows to have exceed the limits of the temperature for a certain time with an accelerated degradation of the paper of the insulation system. And we can see how this is much bigger with FR3 fluids than with mineral oil. And this match with what you said at the beginning, Stefan, will show us these peak curves on the demand, and that can be absorbed. It's not a continuous load of the transformer, it's temporary overloads. And also with the increase in the temperature and the load that the harmonics are creating from the renewables energies. If we see this from the life expectation point of view, if the transformer is working at 65 degrees, we are in a very low loading of the transformer. So the nominal life can be increased between 1.5 and 2 times the nominal life of the transformer. Of course, this comes with a cost. Sorry, the last one, the previous one. No, just to say that this is what we can call a premium transformer. So we are having a transformer that has much more options to be exploited from the utility, from the operational point of view, and it comes with the initial cost a little bit higher. That, according to our experiences, between 10 and 15 higher in cost. But this is true if we are comparing with the base capacity of 65 degrees. If we made a calculation with the overload capacity, the cost per MVA is lower, and then start to make sense, this kind of investment. And now trying to put all this together on the next slide, talking about reliability and resilience of the grid. If we keep the moisture content low and we are increasing transformer life and preserving the dielectric behavior during the complete lifetime of the transformer, we are increasing the grid reliability. Also, having higher temperatures on the winding and the top coil give us more space to absorb these overloads and these temporary overloads that can happen on the network. All of this is expected to have less maintenance and also less outage, because will be a transformer more reliable and resilient. And to summarize, this is a sentence that sounds a little bit US sentence, but it's the best solution with no compromises.
Okay, Roberto, now we learned that the moisture in the paper is reduced by the higher saturation level of the FR3. But this is, of course, important for old and aged transformers to reduce the moisture content in the paper. So is it possible to replace the mineral oil in an already existing transformer with FR3 fluid?
Oh, yeah, sure. The retrofilling of transformers already in use is something that is becoming more important nowadays for several reasons. As you said, one of those reasons is to extend the life of the asset. If the transformer is the mid of the lifetime, by replacing the mineral oil with FR3, we can take advantage of this continuous drying, so we will extend the life of the transformer. It's also true that we also have the advantages of the overload. It can be overloaded, the transformer, by this. And another benefits or reasons to make this retrofilling are the new regulations regarding fire safety, because ester fluid is a K-class fluid, so the fire point is above 300 degrees, and also the environmental friendly properties of the fluid, because it's considered that it's rapidly biodegradable. So there are a lot of reasons that can lead to this idea of replace mineral oil with FR3.
Okay, thanks, Roberto. Let's maybe come back to the fiber optics. You know, quite a long time ago, as I was responsible for the design of transformers, if there was the requirement to install fiber optic sensors, always the question occurred, how reliable is such a technology? So, Peter, can you give an answer on that?
Sure. I would just recommend you to look into the IC. In the IC 676-2 Annex E, it was introduced in 2011. And before you specify fiber optic temperature sensors, go through it. It's kind of 3-4 pages. There's a lot of interesting stuff mentioned there. For example, the direct contact. So it says that the sensor should be placed in direct contact with the insulation material of the winding, which is the paper, or stresses over fiber. So this is the, let's say, most important, from my point of view, the most important part. It is saying attention shall be paid for avoiding dangerous mechanical stresses and vibrations during the manufacturing processes in operation. Because indeed, before 2011, all the suppliers were using a fiber optic wire with a 200 micrometer diameter. After the introduction of this IC, some manufacturers changed from 200 micrometer to the 62.5 micrometer fiber optic wire. And it is a standard from the telecom area. So it's a standard wire. It's much more robust, more durable. You don't need any redundancy or anything. And if you look at the pictures, the transformer guys would recognize that some bending radiuses shown in this picture are only possible with a 62.5 micrometer fiber. It's just because it's so flexible. So let's have a look how the change from 200 micrometer to 62.5 micrometer improved the reliability of the whole system. You see on the left side the 62.5 micrometer fiber, and on the right side the 200 micrometer fiber. So the older one, which in the past everyone was using, now just a few companies are still sticking to the 200 micrometer fiber. The data is from a data sheet from the company OFS, who is a manufacturer of fiber optic wires. So it's a, let's say, third-party data, it's just pure testing data. And if you look already at the transmission loss, you see that the 62.5 micrometer has only 3.5 dB, whilst the 200 micrometer has 8 dB transmission loss. Bending radius for long-term mechanical reliability, which is most important for the customer, for the end customers, is 17 millimeters on the 62.5 side and 28 millimeters on the 200 micrometer side. Bending radius for short-term mechanical reliability is 10 millimeters for the 62.5 and 17 millimeters for the 200 micrometers. So, as already said, the long-term reliability is most important for the end customers. Why? Let's assume there is a fiber installed with, let's say, 25 millimeters bending radius, the 200 micrometer fiber. It will work during the factory acceptance test, but there are already some micro cracks on the fiber which you will not recognize immediately. But after the transportation, after a few years, those micro cracks will work, will rise, and the fiber might not work at the end. So this is why it is so important to look at this long-term bending radius. For the short-term bending radius, it is more important for the transformer manufacturers. It's just when you lead the fiber through the transformer, when you route it with the 62.5, you're just more flexible. And summarizing all that, chances to induce damage from rough handling are 10 times higher with the 200 micrometer fiber. And replacement costs are also much higher with the 200 micrometer fiber. Why? Because I said in the previous slide, the 62.5 fiber is a standard from the telecom, and everything what is a standard keeps you as a customer flexible. Let's assume you need to replace a connector, you need to splice a fiber, an external fiber, or for the manufacturer during the manufacturing process, during the production process, you smash a fiber, you need to splice it. You just go to the local telecom dealer because he knows that fiber, and he can just repair it very easy. So you don't need always to go to the supplier. With a 200 micrometer fiber, you always need to go to the supplier because it's a customized solution. Now going back to the IC, if you look at the data, the pure data, you would say the 62.5 is more according to the IC, and the 200 micrometer is less according to the IC. So coming back to your question, how reliable is the fiber? I would say if you use the right and up-to-date technology, you're safe, and that fiber will work also after 30, 40, 50 years of all your lifetime, and you don't need any redundancy at the end, nothing. So it's a very reliable solution.
Okay, that's nice to hear, and we see also the advantages of knowing an accurate value of the hotspot temperature. So why don't manufacturers not already include this technology in a new transformer?
Oh, you mean if so they include it in every transformer by themselves?
Yes.
Sorry for the joke, but it's like if you bring someone into jail and bring his brother to look after him. So the transformer manufacturers, they're cost driven. Why should they spend more money on stuff which is not specified? I mean, this is why we have such specifications, because what is a transformer? A transformer is 3 windings and a core, and that's it. That's a transformer. But then you need better oil, you need better iron, you need less losses. That's why you specify all that. So it's just to tighten and to tell the transformer manufacturer what you as a customer want to have. So yeah, it's a cost issue why they're not doing it.
Yeah, but if it's a cost issue, how much is the cost of such a technology?
I mean, normally when we were talking to end customers, they say they don't want to spend more than about 5% of the transformer value for monitoring, right? So here I would say the cost for this monitoring solution is about 2% of the transformer value, approximately. So if your transformer is it's like 500,000 euros worth, then it's about, for the whole system, it's approximately 10,000 euros then, approximately. Depends on the number of channels and how precise you want to monitor the hotspots.
Yeah, okay, but we learned that you can apply this technology just in new transformer during the manufacturing process. So maybe it is advisable to install the fiber optic sensors, just the fiber optic sensors, and maybe later, in case there is really an overloading issue in the network, to additionally install the, I would guess, the expensive electronic components, or maybe buy just one monitoring system for a bunch of transformers. What is your experience on that? Is that possible?
So there are thousands of transformers out there with only sensors installed. Exactly what you're saying. So the end customers, they want to benefit from the factory acceptance test by recording the baseline, by controlling design verification during the factory acceptance test. So this is the benefit they have. The other benefit is the investment cost is very low. I mean, if we talk about numbers, per sensor, it's like 300 euros or so per sensor. So that's it. And then you have controlled your design during manufacturing. After manufacturing, you have a baseline for later on. And if we talk about the bathtub curve, which shows that the load of the transformer goes up at the end, and the loading and the isolation gets worse. So then it makes sense to buy a reading unit and start to monitor that specific or that particular transformer. So it's not a new method what you have mentioned, and it's a general practice from end clients to do it like that.
Yeah, we heard during the last SIGRE session in Paris that some quite big utilities already specify installing of fiber optic sensors to use them during the thermal heat run test during factory acceptance, in order to know really is the hotspot factor okay, the winding gradient, and so on. Let's maybe come to the conclusion. So we have seen that sustainability drives innovation in electrification. We see the integration of renewables and electric vehicles, which influences the design and the operation of high voltage equipment. It results in a higher loading, maybe overloading of the transformers, which requires, of course, better knowledge of the hotspot temperature due to the aging, due to prevention of aging of the paper. Natural esters can help to increase the loading capacity. So I have to say thank you for joining us. We start now the questions regarding the the presentations. I have here some questions from the audience. Maybe let's start with questions related to FR3. Related to FR3 and lifetime, is there any investigations on the change of permittivity for insulation in tongue delta during the operation?
I think I should take this one, right?
Yes. Sorry.
Yes, we have made several tests on FR3 fluid, on aging vessels, sealed vessels tests, and we have monitored all the properties of FR3 fluid in contact with materials that are usually used inside the transformers. And for example, the question was related with permittivity, and you can say that permittivity remains stable during the complete lifetime of the test and the process of the transformers. And regarding the other properties, talking tangent delta and this kind of measurements that are made on the transformer, we didn't see differences on the normal behavior with mineral oil, meaning
Roberto?
that yep.
Yeah, if you allow me, this is Alan, just to offer some help here on this one. So the permittivity, the dielectric constant of FR3 is around 3 at 9 degrees, and mineral oil is 2.2. So there is a different distribution of electrical field and stresses inside the transformer due to that. In general, reducing the stress in the fluid and increasing the stress in the solid insulation. But when we bring in perspective that the dielectric constant of water would be around 80, we see that an increasing of moisture content in the solid insulation will have a much stronger effect, and will still be detected and lead to a variation of tan delta power factor in the same way that it does in a mineral oil unit. So the answer would be that there will be a different reference value, a starting value, but the variation of power factor along time will allow identifying when paper is increasing on moisture content and getting wet.
Yeah, thank you.
Okay, thank you, Alan, for giving us this answer. There's also the question for FR3 retrofit. What consideration should be taken due to the higher viscosity of the fluid?
Sorry, Stefan, I couldn't hear you. Could you repeat, please?
For FR3 retrofit, what considerations should be taken due to the higher viscosity of the fluid?
Oh, yeah. Well, the viscosity of FR3 is higher than mineral oil, and we have seen in our experience that viscosity is not only the driver, the property to look at when we are talking about heat transfer. So we need to take into account viscosity, but also heat transfer and specific heat of the fluid we are talking about. And as specific heat and heat transfer have higher values on FR3, this compensates somehow the lower viscosity, the higher viscosity of the fluid. I can say that in distribution transformer, we are seeing an increase in the top oil temperature around 3-4 degrees for distribution transformers, which is still pretty far from the limits for that value on the standards.
Okay, maybe one last question regarding FR3 before we return to the fiber optic sensors. Loading the transformer beyond nameplate capacity will increase the losses, of course, due to the higher temperatures. thus making my grid less efficient. Is this true?
Not exactly. We need to take into account not only load losses, but also no load losses of the transformer. To match peak demands on the grid, you have two options. You use a bigger transformer with higher no load losses, or you can use a smaller transformer and overload it periodically in these 2-3 hours per day from time to time. So as you have shown in the beginning, the difference between the peak and the flat part of the curve and the demand curve is between 2 and 3 times. So to absorb, by overloading the transformer during these hours, we are keeping node load losses at lower value, meaning that to make the assessment of the grid, we should take a 1 year period and see how much each one of the losses influence on the energy that disappear on the grid.
Okay, so maybe Peter, regarding fiber optics, does it make sense to equip distribution transformers, so smaller transformers, with fiber optic sensors?
Well, if you would ask me this question 10, 15 years back, I would say not really. But nowadays, a small distribution transformer can become more critical than a grid transformer. So distribution transformers with a lot of consumers, which are not only consumers, but also now producers of energy, are much more overloaded. So just to avoid outages, we see also many companies now equipping distribution transformers with fiber optic sensors. Of course, you don't take, like in a grid transformer, 8, 12, or for example, we have also customers with 24 sensors for a transformer. You maybe take only 3 sensors for one transformer, and can do controlled overload of this distribution transformer. So it nowadays, with the dynamic load and the reverse power flow which we have, it makes sense.
Okay, there's the next question. What's the margin of error between direct contact of sensor versus non-direct versus relative calculation? So, of course, I showed in my first figure the calculated hotspot temperature. So can you give us some experience? Is this calculated hotspot temperature accurate compared to the measured value by fiber optics, or what is the experience during heat run test? Does it show sometimes discrepancies between the measured hotspot temperature by fiber optics and the design value, or the value which is determined by during the heat run test by measuring the resistance of the copper of the winding?
I mean, I need to be careful when I answer this question. Let's say most of the European transformer manufacturers, the calculations of most European transformer manufacturers, because I can only talk about Europe, I cannot talk about other areas in the world, fit also the reality. So if you buy a transformer from somewhere in Europe and you want to control, you want to do design verification, then it's pretty sure that it will fit the reality. But if you recognize a transformer manufacturer, which is, let's say, if you have a new transformer manufacturer for your specific design, which you maybe don't trust that much, or if it's a transformer manufacturer, for example, who is doing smaller transformers, and now he wants to enter higher level transformers, so it's something new for him. So it's for him building a new design. Here we saw discrepancies, and we had also clients who specified because of that. So it was a new transformer design. This transformer manufacturer provided for him. It was also a new design for the transformer manufacturer. So he specified the fiber optics to do design verification, and if there will be some gap between reality and calculation, the transformer manufacturer had to pay some penalty to the client. So at the end, the first lot of transformers had this discrepancy, but the next lot was, I would say, nearly perfect. So it was a benefit for the end customer to control what he's buying. So going back to your question, I don't have real numbers. So we say sometimes, like, let's say higher than 3 degrees Celsius, discrepancy is difficult to accept. But yeah, I hope I could answer it somehow.
Okay, thanks. Maybe let's come back to the tricky points. And with FR3, I have this question for you. Why transmission utilities still hesitate about replacing mineral oil since natural esters are much beneficial? That is a question, and I maybe can add, this goes maybe in the direction of dielectric strength of natural esters. So what can you tell me regarding this dielectric strength of natural esters, Roberto?
Well, the only thing that I can say is I'm not sure why they haven't changed yet, but I will like to see them in the near future. And regarding dielectric behavior of natural ester, all the tests that we have been done in the past and during all these years has shown that the dielectric strength of natural ester is at minimum equal or superior, depending on the test performed, that mineral when compared with mineral oil.
Roberto, maybe if you allow me also to join here, I have been involved with a series of tests we did with University of Stuttgart with Professor Tenbohlen and his team in the past. So we compared the dielectric capacity, the breakdown voltage in several different electrode configurations, and we identified that when you get to an extremely sharp edge, a divergent field condition, there would be a difference on the breakdown voltage for the impulse test, and the sharpness level would be a diameter or edge radius lower than 0.5 millimeter, which is typically not acceptable in any transformer. So the typical or the normal manufacturing processes and tolerances should avoid getting to the field enhancement factor where the breakdown voltage between natural ester and mineral oil would not match. So for all the typical constructions that we have in a well-designed and manufactured transformer, the dielectric behavior would be equivalent. I think that's the main aspect is it takes time for people to get comfortable with new technologies and starting adopting. We can share some numbers, especially here in US, where we would estimate something around 12 to 14% of the new transformers already being filled with FR3. The number is much smaller in Europe, but we hope it will grow.
Maybe I can ask you the question. you know, in the early times of using natural esters, it was used for medium voltage transformers. But nowadays, the rated voltage of the transformers equipped with FR3 or filled with FR3 still increased. What is the highest rating and voltage at the moment for power transformers filled with FR3?
Well, the highest that I know and is installed here in Europe is a transformer in Germany that is if my memory recalls correctly, is 420 kV on the high voltage side, and the rating power is around 300 MVA, if I'm not wrong.
Yeah. So in Germany, these type of transformers are tested with a lightning impulse of 1,425 kV. Yeah. So this transformer passed obviously the test. So you know, I would say in an environment which is strongly based on experience, of course, using new materials and technologies needs always some time to, let's say, to collect some good experience in order that others follow this way. But as far as I heard, there were up to now no problems with that transformer in that voltage class by using these natural esters. So that was possible.
Just adding one piece of information, Professor. During the development of the bushing electrode for this 420 kV unit, the type tests require increasing in IC the voltage class in up to 2 levels. So we had the bushing electrode being tested to the level of 2050 kilovolts impulse. That would be the first level of basic impulse level for a 765 kV AC. So we had tests going all the way up to 2000 kV impulse.
Yeah, perfect. So let's come maybe to the last questions. There are already some other questions, but we are running out of time. So let me. We have one fiber optic, and poor point is also okay. Let's keep it with these two questions. First question regarding fiber optic sensors: how do you position it to the hottest spot? Short answer, Peter, please.
So, I mean, how do you know where to position the fiber optic sensors? And this is the transformer manufacturer who knows where to position. So he does the calculation, he knows where the hotspots are, and this is where he positions his sensors.
Okay. So, and then last question regarding FR3. In Canada, the main concern for using natural ester-based transformers is due to the poor point. Have you had any data from the field transformer in freezing condition and operating safely? So I think this question occurs quite often. Yeah.
yeah. And yes, we have plenty of references on that. The first point here, is that the poor point does not reflect the actual behavior of conditions of the transformer working in the field. It's a test lab that is not reflecting the real conditions. And yes, we have a lot of references in the North Canada, north of Sweden and Scandinavian countries with very, very low temperatures and starting working without any kind of problem. And I think we are out of time.
Yeah, this prevents me from second question. So, but Roberto, thanks a lot. You know, I have shown here now our 3 email addresses. So in case of questions, you can approach all our presenters today directly with emails and ask them these questions. I would like to thank, of course, the presenters for preparation of their slides and giving us her knowledge and sharing their knowledge with us, and also to the audience for all these interesting questions. And I hope to see you soon somewhere on a conference in person. Thanks a lot, and have a good time. Bye.
Thank you very much.
Bye-bye.
Bye-bye.